Good evening, all. Welcome to today's live discussion session for the NPTEL course Water Supply Engineering. I am Reshma R, PMRF Research Scholar from Hydraulics and Water Resource Engineering Division, Department of Civil Engineering, IIT Madras. Let me share my screen. Hope it is visible.
Yes, it is visible.
Okay, so let's start the session. Question number one. The geographic information systems in smart water management systems is primarily used to option A, conduct risk management exercises, option B, collect and transmit information in real time, option C, store, manage, manipulate and analyze spatial information, option D, all of the above. So you can type in your answers in the chat box. So what is the primary need of including geographic information system or GIS in smart water management systems? Okay, so let's see what is the correct answer. Yes, the correct answer is option C, store, manage, manipulate and analyze spatial information. That is the primary use of GIS in smart water management systems. So, Geographic Information System or GIS in smart water management systems is primarily used to store, manage, manipulate, and analyze spatial information. So, here this is particularly applied for asset mapping and asset management, for fully integrated network models, as well as environmental data analysis and management. Coming to question number two, which of the following is a major application of the SCADA systems in smart water management? Option A, pressure management. Option B, pump station optimization. Option C, both A and B. Option D, integrated network modeling. So, what is the major application of SCADA? Okay, so the correct answer is option C, both A and B. That is, the major application of SCADA in the case of smart water management system includes pressure management, pump station optimization, water treatment plant control, sewage treatment plant control, environmental controls, reservoir controls, and flow controls. So the control of different components in the water network or water distribution network, along with the pressure and pump management. That is the major application of SCADA system. So, when we consider the technologies that are available for smart water management, we can see that the components include digital output instruments, that is meters and sensors, digital meters and digital sensors, wherein the required data is displayed in a digital form. It can be a meter or a sensor. Then we have SCADA system, that is supervisory control and data acquisition system. Then we have GIS, that is Geographic Information System, and the required softwares to run these programs. So the first one, that is digital output instruments, which includes meters as well as sensors, are used to collect and transmit information from the real time. That is like in the real time system, that is in the day to day basis. If we need the data, if we need to collect as well as to send the data to a control location, for that purpose we will be employing digital output instruments. For example, we have rain gauges to measure the intensity of rain, flow meters that measures the discharge or flow rate. For example, flow meter installed in a pipeline will measure the flow rate or the discharge through that particular pipeline. Then water quality monitoring to monitor the quality of the water that is being circulated, and other environmental data. Another one is acoustic devices for real-time leakage detection, as we saw in the previous classes. Then video cameras for asset management, smart water meters for measuring consumption that is employed at the consumer end, so that we can keep an account of the amount of water used by each individual consumer, and then we can give a fixed pricing or a user dependent pricing for the water consumed. Then we have pressure monitoring, which helps in leakage detection and pump optimization. So the next component is supervisory control and data acquisition, that is SCADA system, which is used to process the information and remotely operate. That is, we can install this particular system in our control station, and then it can enable us to remotely operate and optimize the system and process in the field. So through this, we can control the pressure, pump station optimization, and different components such as water treatment plant, sewage treatment plant, environmental control, reservoir flow, etc., as we saw in the previous question. Then we have geographic information system, which is used to store, manage, manipulate, and analyze spatial information, as we saw earlier. So it is used in asset mapping and asset management, environmental data analysis and management, and fully integrated network models. Last, we have the software that is required to handle all these components. That is to store, use, and report the data. That is to process the data. We need some software that will help us to control these other components. So there, usually it is integrated either with the GIS or SCADA systems, and it helps us to arrive at an improved decision making. Also for smart metering and billing, hydraulic design and optimization, water resources as well as hydrological modeling, all these can be done using different types of softwares. So coming to question number 3, a positive displacement meter is used to, option A, measure small volumes of water at low flow rates. Option B, measure water pressure in network pipes. Option C, detect TDS and conductivity in water. Option D, all of the above. So, for which purpose we use a positive displacement meter? Okay, so the correct answer is option A, that is to measure small volumes of water at low flow rates. So, positive displacement meters are used to measure small volumes of water at low flow rate. This is a type of traditional flow meter. This is also known as displacement water meter. Positive displacement meters are otherwise known as displacement water meters, and these are mostly used in residential application and small scale commercial operations. So mainly they are of two types. One is with an oscillating piston, and the other one is with a notating disc meter. That is, in these types, what happens is either the piston or disc, depending upon the type, will get displaced or moved as water flows through the meter's main chamber. So, as the water flows, that particular piston, in the case of oscillating piston, and the disc, in the case of disc meter, will get displaced or moved according to the water flow. So the moving parts measures the volume of water, and then by appropriate amount the register, the reading will be, the reading on the meter will be increasing. Another type of traditional water flow meter is the velocity water flow meter or internal capacity meters. So these determine the volume of water that has flowed through the meter based on the speed of flow. Earlier, it was based on the displacement or movement of piston or disc, but in the case of velocity water flow meter, the measurement is done based on the velocity or speed of flow. For that, either they use a multi-jet, that is impeller based, or a turbine for large applications, or compound, that is both multi-jet and turbine for highly variable needs. Okay, so now question number 4. Identify the correct sorry Identify the correct statement regarding automation in water supply systems. Option A: software components are more crucial for the automation process. Option B: automation encompasses both monitoring and control of key system components. Option C: remote monitoring is typically achieved through advanced GIS based systems. Option D: all statements are correct. So, which is the correct statement with regard to automation in water supply systems? You can type in the answers in the chat box. I'm getting only a few messages actually here. Okay, so let's see which is the correct option. The correct answer is option B. Automation encompasses both monitoring and control of key system components. So, automation can be achieved for both monitoring and control. Both hardware as well as software components are equally crucial for the automation of water supply systems. And remote monitoring is achieved using a programmable logic controller, supervisory controller, and data acquisition, that is SCADA systems, and global systems for mobile communication. So, the key necessity for automation of water supply systems is installation of sensors, that is to measure the flow, pressure, as well as quality, to control tools at strategic locations, which are then remotely monitored and controlled, usually using a GIS and SCADA system. So, the scope of automation in water supply is like automation we can apply at several stages. Starting from the raw water extraction till the consumer end, we can apply the automation at several stages. So, seeing raw water extraction, we can monitor and control the pumping of raw water resources, that is the pressure, quantity, everything we can control. Another thing is quality, monitoring of raw water quality. So, coming to raw water extraction, we can control the quantity, quality, pressure, everything of the water that is pumped out from the raw water sources. Second stage is drinking water treatment, wherein we can monitor and control the treatment units. For example, aeration unit, flocculation unit, filtration unit, all these things we can monitor and control. Also, we can estimate the chemical doses required for that particular process. We can control the quality and quantity of this particular chemical being added for the process. Once it is treated, we can monitor the water quality of the treated water. We can monitor the water levels in clear water reservoir, and we can control the pump of this treated water as well. Next stage is water distribution. So there also we can control the pumping station, the quality, quantity, as well as the pressure at which it is being pumped. We can monitor the inflow that is coming from the treatment plant, the amount that we are distributing, the pressure at which the distribution is done, the reservoir levels at regular intervals, all these can be monitored and controlled. Different valve operations can be controlled, as well as the quality of the water being distributed can be controlled. So, question number 5. The principal function of remote terminal units of SCADA systems is option A, presenting processed data to a human operator for monitoring and control of the process. Option B, converting sensor signal to digital data and sending digital data to the supervisory system. Option C, receiving the sensor data and executing logic based operations resulting in processed outputs. Option D, all of the above. So, which is the principal function of remote terminal units of a SCADA system? Okay, so the correct answer is yes, option B, that is converting sensor signal to digital data and sending the digital data to the supervisory system. So, the remote terminal units used at remote sites, for example, pump station, storage tank, valve vault, and treatment facilities, are connected to the sensors. So, they receive the data from the sensor and they convert that to digital data, which is later on sent to programmable logic controllers, which is in a control room where one executive professional or a personnel will be available so that to execute logic based operation and give out processed output. So, at the end, the operating personnel will be able to view the entire process and perform the control action through human machine interface. Question number 6. Dash executes logic based operations resulting in processed outputs. Allow operators to view the entire process and perform control actions through the display at option A, remote transmission unit, human machine interface. Option B, programmable logic controller, remote transmission unit. Option C, human machine interface, programmable logic controller. Option D, programmable logic controller, human machine interface. So, which is the correct answer to fill in the blanks? Okay, so the correct answer is option D, programmable logic controller and human machine interface. The same sentence we had seen earlier in the previous question. So we will look some like Okay, we'll see what is SCADA and what are the functions it is performing. So, SCADA is basically supervisory control and data acquisition system. So, it's actually an automation process wherein there are multiple components. There are hardware components, software components. So, the primary aim is to collect the data from the sensor, process it into digital outputs, monitor it properly, do logical operations, and then to record the events in a log file. So these SCADAs are actually computer systems. So what it does is it gathers and analyzes real-time data collected by sensors or meters, and then it is transferred to the supervising personnel. So we have PC-based workstations and programmable logic controllers, which are posted in a control room. And then we have remote terminal units fixed at remote sites, such as pump station, storage tank, etc. And the SCADA architecture is something like this. That is, there are monolithic SCADA, which was first generation SCADA, and then we have distributed SCADA, that is the second generation SCADA. So the monolithic SCADA was developed during times when ordinary network services didn't exist. So it was like separate systems were there, interconnection were not there. But later on, RTU vendors designed wide area network so that in between, like among the RTUs itself, communications became possible. Initially, it was each individual RTU was giving data to SCADA master without any connection among them. And this function is limited to flagging of operation in case of emergency and monitoring the sensors. But when it comes to the second generation or distributed SCADA system, it's actually through a LAN network, that is local area network. The data is being distributed between multiple stations. Command processing and real time data is shared to perform control operations. So here the cost, size, everything is reduced, but standardized protocols are not there. And hence not many understood the security of the SCADA system also. So then came the third generation SCADA, that is networked SCADA, which is mostly used in the present days. So here we communicate over wide area networks instead of local area network or LAN. So we have internet protocols, as similar to internet protocols and all. We have the proper protocol, security system, everything here. Fiber optic connections or Ethernet is used for data transmission, and since the internet linkage is coming in between, vulnerability of the system is increased, and usually this is protected using security techniques, standard protocols, etc. And then last we have the IoT SCADA systems or the fourth generation SCADA systems. So it is actually a reduction in infrastructural cost. So here we have cloud computing option, so that the management, maintenance, everything becomes more easier. So directly in the cloud, each RTU can report the data, then control algorithms can be implemented that are often used on traditional PLC. Everything can be done in the cloud computing section itself. So coming to the key components of a SCADA system, first one is the human machine interface, which helps the operator to control, view, and manage the processed data. Then we have a supervisory computer system, which gathers the data from sensors and meters and controls the process. Then we have communication infrastructure, that provides connectivity between the remote terminal units and the supervisory system. So remote terminal units, as we saw earlier, is will connect to sensors and meters, will collect all the data from them, and then it will send that to the supervisory system through this communication infrastructure. Then we have programmable logic controller, which are electronic brains that scan the lines of custom code to execute predetermined logic based on the inputs from the readings of the sensors, so that the output can be controlled at the end device. These are the key components. So we have the sensors here, which are connected to the RTU. Then through a communication network we have it connected to the master link, SCADA master. So this is an example of a PLC cabinet, HMI display, human interface display, and the control panel, etc. So question number 7. An essential function of a typical smart meter is option A, measurement of the target parameter, option B, storage and display of the measured data, option C, transfer of the recorded data, option D, all of the above. So which is the essential function of a typical smart meter? Which is the essential function of a smart meter? Okay, so the correct option is option B, all of the above. That is, in addition to the measurement of that particular target parameter, they are also enabled to allow continuous reading, storage, display, and transfer of the measured as well as recorded data. So these are basically tools that we use to measure the water use, that is water consumption, as in the case of a water meter in our home, then the pressure at the consumer end, quality. So on their own, they cannot influence water consumption or flow pattern or water quality parameters. It just reads, records, and stores the data that is being collected. So smart meters and sensors as intelligent monitoring solutions. So as we saw, smart meter is a standard or conventional meter. To make it smart, it is attached to a device so that we can have continuous reading, storage, display, etc. A normal meter will display it, so to make it smart, we are adding some components that enables to have a continuous reading, recording, everything, but still it doesn't have any influence on water consumption or flow pattern. Rather, it is the high frequency information from these meters that is used to make the appropriate decision on the management level. So when we are putting a smart meter, obviously cost will be additional, but the benefits are much higher than the increase in cost. So this is a example block diagram of a smart water meter connected to different sensors, and then the processing unit and the output units. So question number 8. possible disadvantage of smart water supply systems that hinder their implementation could be: option A, higher capital cost; option B, higher operational cost; option C, higher manpower cost; option D, all of the listed options. So, what is the possible disadvantage? Yes, it is the higher capital cost, option A. So, installation or the capital cost for smart water grids is higher due to the additional cost of meter, sensor, automation system, all these components that make it smarter. But their operation cost is often lower because we need less manpower here. Everything is automated. So, frequent lab visits can be avoided, labor charges can be reduced. So, the operational cost is lesser, but the installation or capital cost is higher. Question number 9. The level of automation in water services presently practiced in India is: option A, total automation of water distribution networks; option B, fully controlled water distribution networks; option C, fully monitored and controlled smart water grids; option D, partially or fully monitored and controlled water treatment system. So, which among these is adopted in India? Yes, it is option B, that is partially or fully monitored and controlled water treatment systems. So, in several cities of India, we have partially or fully automated systems, and no city have a completely automated water distribution system network or smart water grids. So, the trend is like, um, the automation is only at few places. That is mostly to the monitoring of flow or pressure in the bulk flow meter or reservoir level sensing, etc. The total automation is nowhere in practice because of the huge infrastructure upgradation required. For Indian cities, it is actually already the water distribution networks are laid long back. So, if we have to make it smarter, we may have to upgrade many components, and that too in a huge quantity as well. So, the smart grid system for complete automation is at trial and testing stage, even in most developed cities across the world as well. So, question number 10. Nation propagating the use of near smart water grids infrastructure in their water services is: option A, Australia and Singapore; option B, South Africa and Singapore; option C, Korea and South Africa; option D, India and South Africa. So, which all nations propagate the use of near smart grid water infrastructure? Yes, it's option A, Australia and Singapore. So, the two leading countries in deploying smart grid water infrastructure are Southeast Queensland from Australia and the Water Supply Network Department from Singapore. So, the global trend of smart water grid technology is like that, that is Southeast Queensland Water Grid from Australia and Water Supply Network Department from Singapore are the two leaders in deploying near smart grid water infrastructure. There are many new proposals being considered and attempted. For example, smart water grid systems for smart cities in India, smart water grid project funded by Korea Ministry of Land, Infrastructure and Transport, national smart water grid from the USA to alleviate water scarcity problems in the Midwest USA. So that's the end of today's discussion questions. So if we have any doubts, We can discuss those.
Will you please repeat question number 3 and 6?
3 and 6. One second. Okay. Yes, so 6 is like the questions of fill in the blanks type of question. That is, dash executes logic based operations resulting in processed outputs and allows operator to view the entire process and perform control actions through the display at. So in the earlier previous question we saw what is a SCADA system and how it is performing. So it has a remote transmission unit which collects the data from the sensor or meter and converts to digital data which is sent to the programmable logic controller, and there the logic based operations will happen and the results will be displayed through the human machine interface. So the answer is option B, that is, in programmable logic controller. In the programmable logic controller we have the logic based operations happening, and in the human machine interface we have the results being displayed. Is it clear?
Yes, it is clear.
Okay. So, and the other one was third question, right? Yes. So the third question is like a positive displacement meter. So we have different types of water meters. Mainly the traditional type of water meters are, one is positive displacement meter or displacement water meter, and the second one is velocity water flow meter or internal capacity meter. So the difference is, in the case of positive displacement meter, they are primarily used to measure small volumes of water. So here what happens is there will be a moving component, either a piston or a disc, which moves in accordance to the flow of water that is in the meter. So depending upon that movement, we'll measure the volume of water flowing through it. Whereas in the case of velocity water flow meter, as the name suggests, the measurement is based on the velocity or the speed of flow, for which we will be using multi-jet or turbine or compound. So if it is an impeller base, we will use multi-jet. For large applications, we will use turbines, and for highly variable needs, we will use compound. So that is the two types of traditional water flow meters.
Okay, that means in both the cases, volume of water is measured, but
Yes,
in first case, it is with respect to displacement, and in second case, with respect to velocity of flow.
yes, correct.
Thank you.
Any other doubts? Anyone else? So if there are no other doubts, we can close the session for today, and again we can meet on next live discussion session. So thank you all.